Hi. In this section, we're going to start talking about variational autoencoders, which are one of the main paradigms in deep learning. And I want to start by talking about latent variables. So I want to talk about the problem of a child learning to understand speech sounds in terms of words and phonemes. So the child hears a bunch of sound waves and eventually starts hearing it as sequences of discrete phonemes or maybe even words. So we would like a machine learning algorithm, a deep learning algorithm, to be able to do this, right? To be able to start from just raw sound and acquire an interpretation of that sound as word sequences or phoneme sequences. And this phoneme sequence is a latent variable in the sound waves. By a latent variable, I mean the material we're learning from does not provide any labels. So it's latent in the data. And I'm going to use Y for the raw sound, the thing we can observe, and Z for the latent variable, which is the thing we want to recover, like the phonemes or word sequences. And just so this happens all the time. There are lots of examples of this. So the latent structure might be the parse tree of a sentence, or it might be a segmentation of an image, or a depth map, or some 3D representation of the image, or it might be a class label for an image. We would like to be able to take just the images or just the sound waves and recover this information. So we want the latent understanding to emerge from the data, and it's latent. Now, in VAEs and in a lot of probabilistic modeling, we think of the latent information as the causal source of what we observe. So you have an actual physical scene out there and a camera, and the physical scene causes the image. So you might want to say, well, the scene, we want to model, ultimately what we want to do is model the reality, because that's the real source of the data, and then get a probability model of reality and then understand how it causes our sensation. So we think of Z as the causal source. And we're going to write the probability, or we're going to formulate our models in terms of a prior probability over the source and a probability of what we observe, our sense data, given the source. So this would, in language, the child might have some language model, some probability distribution over strings of discrete words, and then some model of how the sound can be generated for a given string of words. Anyway, this is the structure of the model we're going to be investigating. We have a prior over the latent variables. So we've got, it's called the prior. The model's probability on the latent variables is called the prior. The probability of the latent variables given our sensation is called the posterior. The sensation is the evidence, the sound wave is the evidence about the word sequence, and it's the word sequence that we care about. At least that's the intuition. So this is the way the models are formulated. And then there's given this model defines a joint distribution on Z and Y. That joint distribution on Z and Y has a marginal onto Y, right? So this is the model's probability distribution over sound waves, over the sense data. We're going to assume, in formulating variational autoencoders, we're going to assume that this prior probability over the word sequences, over the latent variables, is something we can both calculate for a given sequence and we can sample from. So that's true of language models. And we're also going to make the same assumption about the probability of our evidence, whatever our evidence is, given the latent structure. So this would be the sound wave given the word sequence. So this is true for nice autoregressive models. It's not true in general, right? If your model was a deep graphical model, these would be things you couldn't compute. But in today's unit, we're assuming these things are sampleable and computable in this structure. We can sample and compute the prior over the latent variable, and we can sample and compute the evidence given the latent variable. Okay, so our model, we now have a model, right? The model says there's a prior probability over the word sequence and there's a probability of the sound wave given the word sequence. By the way, I should have said throughout this unit, I'm going to be using discrete probabilities everywhere just to make my life easy. And so I don't have to worry about, unboundedly negative log densities. Anyway, so we have a model. Our model is defining a probability distribution over the evidence, over the sensations. And we would like to just use cross entropy, right? That's a sensible thing to do. So we would like to find parameters of our joint model, a probability distribution over the word sequences, and a probability distribution of the sounds given the word sequences that best explain the sound waves we're hearing, right? So all we hear are sound waves. We're looking for a theory of the sound waves. We're looking for a theory of the sound waves that best explains the sound waves. What does it mean to best explain the sound waves? It means the cross entropy of our model to the sound waves, the cross entropy from the actual population of sound waves to our model of the sound waves is minimized, right? We want to have the most accurate probability model over the sound waves. Now there's a problem here. We would like to minimize this cross entropy, but this marginal onto y is intractable. Just to think about this, if I give you a sound wave, sometimes they're noisy and you can't, you don't know what was said, like in a song. Sometimes you're confused about the lyrics, but if somebody tells you the lyric, then you can hear it suddenly. You can verify it. So what that means is that this search over the word sequences to explain this sound wave is hard, right? There are a lot of possible word sequences, and you might have to search them, and you might not think of the right one. So computing this marginal over y would at least involve, finding the likely word sequences that generate that sound. And when I hear a lyric and I think it says something weird, it's because my language model is telling me what I'm interpreting that word sequence as doesn't make sense. But so finding the z that explains the y, it can be an NP-hard problem. It's an intractable problem. So computing this marginal is intractable. So that means that this cross entropy is not easy to use, right? Because we can't compute this in the modeling framework we're in. So VAEs variational autoencoders are going to sidestep this intractability. And they're going to sidestep the intractability by assuming I've got an inference algorithm it's an algorithm that just will compute the word sequence given the sound. So this doesn't have to be the actual distribution. It's just some arbitrary almost probability model for extracting the word sequence given the sound. It doesn't have to be right. It doesn't have to be correct according to the joint distribution that we defined. It's just another piece of the model. But the idea is we're going to add this piece of the model in our optimization. This is going to now be a tractable model such that given y, I can sample z, which is not true of the true marginal in the model we've defined. So this is just some tractable way of computing and sampling z given y, possibly unrelated to the model, the other components of this model that we're building. But we're going to treat that as an approximation to this in the equation. And here's the fundamental theorem. It's a simple derivation. I love true facts theorems. This is the elbow, the evidence lower bound. So this is the essence of variational autoencoders. And what we're trying to do is minimize across entropy. Minimizing across entropy is the same thing as maximizing the log probability of the evidence. Instead of minimizing the negative of this, we're maximizing it. That's the way it's normally formulated. That's the way the elbow is normally formulated. So this first step is very unintuitive. I don't know how you would anticipate making this first step in the derivation. But if you look at this thing inside the log, it's the log probability of y, right? And multiply and divide by the same thing. So that's obviously the same as that. And it doesn't matter, this expectation doesn't matter because no matter what we pick here, this is the log probability of y because that cancels. So I don't know how you get that first step, but let's take that first step. This equation is true. Now, if I take this equation to be true, all I'm going to do is I'm going to multiply and divide by some random model that's trying to do inference of z from y, right? And then I can, if I multiply and divide by that, I separate the log into these two pieces. Okay, now what happens is this piece of the log now, because this expectation is over this distribution, this piece of the log is a KL divergence, which has to be non-negative. And that means this other piece of the log has to be greater than or equal to the sum of the two, right? So, I'm sorry, less than or equal to the sum of the two. This piece has to be smaller than the sum. So that means that the sum, which this is, has to be less than, God, this term has to be less than the sum, which has to be, and the sum is this. So this has to be less than this log probability. And this is the evidence probability. This is a lower bound on the evidence probability. So this is an evidence lower bound, the elbow, the evidence lower bound. Okay, so, I sort of ignored a step when I went from here to here. I should have pointed out that this is the model written backward. Our model is actually probability of z times the probability of y given z. But this expression is the joint probability. And when I write the joint probability, I can then unwind it, if I want, into the probability of z times the probability of y given z. So I should have pointed out that I was replacing that by the joint probability. Okay, that probably went by pretty fast. I don't know what to do about that other than to play with it a little bit more. If you have taken an introduction to machine learning, you've probably seen the expectation maximization algorithm, EM. EM is probably the most difficult thing to get your head around in an introduction to machine learning. And I'm not sure I'm going to make your life any easier, but I'm going to point out that EM is exactly alternating optimization of the elbow. So this derivation is simple enough. It should convince you that this is true, okay? So if this is true, what I'm going to do is I'm going to write the variational autoencoder is going to be just an optimization of the elbow, right? So what we're going to do is we're going to convert it to negative log probabilities just so that I can take we're used to minimizing. So this thing here, the objective is to maximize the probability of the evidence. We want to minimize the negative log probability. So I've converted it to a negative log probability. So we're minimizing, this is the negative of the elbow. We're minimizing the negative elbow. The other thing I've done is I've separated the parameters such that my inference algorithm, my arbitrary inference algorithm to infer the word sequence from the sound wave, I've written with parameters psi, and the joint model I've written with parameters phi. Up to now, I've always been using phi because they're cooperative, and you want to think of all the parameters as being in a big bundle of all the parts of the model so that they can share parameters. But here, I'm going to separate these parameters so that I can talk about alternating optimization. So what we're going to do, so phi is the parameters of the model, and psi is the parameter of the inference algorithm. It's inferring the word sequence from the sound. And what I'm going to do is alternate the minimization between phi and psi. Okay, and when we alternate that, if we assume that our model is simple enough that each one of these optimizations individually can be done exactly, then you get exactly EM. Okay, so what happens in EM is I take the model that's doing the inference, and this is an expectation over the Z's as defined by the model taking the inference. And I do an exact optimization of psi. Now it's possible to show then when you exactly optimize psi, the optimal value of the generator is exactly the conditional probability defined by the model. I should have pointed that out on the previous slide, that if these agree, if this is exactly the conditional probability here, then these cancel and this just becomes the log probability of y. Anyway, the optimum when I optimize psi is the conditional probability defined by phi. So what happens is the optimum here, I can take this min and do it holding phi fixed. I'm alternating the optimization. I just do this holding phi fixed, and then the optimum is p phi, under the joint distribution defined by this, it's the conditional probability of z defined by y. That's the optimum value of this. And then what I'm going to do is I'm going to alternate. I'm going to hold that fixed and optimize this. And when I hold that fixed and optimize this, that's going to give me the next value of the parameter setting. So I'm holding this fixed. Phi t is being held, this is being held fixed. So the sampling over z is being held fixed. That means this denominator is being held fixed. So the argmin over phi is just the expectation over a fixed distribution on z of minus log probability phi of this joint distribution. And that's exactly the EM step from phi t to phi t plus 1. It's exactly this alternating optimization. So the elbow and EM are sort of intimately related. EM is a special case of the elbow, but the elbow and variational autoencoders are much more general. You don't have to have these tight constraints on the model that these optimization problems can be done exactly. In EM, you're assuming that each of these can be run to completion each of these alternating steps can be run to completion exactly, which is a very strong constraint. So why is this called an autoencoder? Can we interpret this as an autoencoder? So here's the elbow. The elbow, this is what we were writing before. This is our inference algorithm, arbitrary inference algorithm, and the log probability of our waveforms, of our evidence, is greater than or equal to this expression, no matter what this is, right? But if we minimize this exactly, then these are equal. So this is actually equal to the inf over all models if we were universally expressive. So if we were universally expressive, we're going to get exactly that answer. Now, I'm going to take this and I'm going to expand it the way that we've been modeling it. I'm going to expand this joint probability as the probability of z times the probability of y given z. And then I'm going to take the probability of y given z and pull it out. And I'm also going to switch to minimizing. So I'm going to take the negative log probability, and now I'm minimizing, and that sign flips. So this is this is a minimization of the cross entropy, and we're saying the minimization of the cross entropy is upper bounded now instead of lower bounded by this expression. And this term of this expression now is a KL divergence node. We eliminated a KL divergence in proving this inequality, but what we derived has a piece that's still a KL divergence. And that means that Z, remember that differential entropy is problematic. Negative log of a density can be arbitrarily negative. But KL divergences are meaningful for densities. So this says that we could take Z to be continuous, and we're in good, and it's still legitimate, right? It's not diverging to negative infinity. So this piece is a KL divergence, and we're left with this piece over here. So this is the way to write a VAE that also makes it obvious that you can optimize it, because we're assuming that this is sampleable, and we're assuming that these can be computed, right? So we're assuming that I sample from here, I sample Y from the population, I sample Z from here, and I can compute now all the terms over here. And if I can compute them, I can take their gradient, and now I've got something that I can run SGD on. and it's an upper bound on the cross entropy. So I'm really being very faithful to the cross entropy objective function here. I'm minimizing an upper bound on the cross entropy. And if my modeling is universally expressive, I'll actually get to the entropy of the evidence, just like with cross entropy. Now, we did a unit a bit ago on rate distortion autoencoders. And this unit has been looking at things very differently, right? It's been looking at these latent variables as having some important semantic meaning, like the word sequence or the geometric structure of the world that led to this image. Nonetheless, variational autoencoders are mathematically essentially the same thing as a rate distortion autoencoder. So let's see how that works. Even though there's these different ways to think about what problem is being solved. In a rate distortion autoencoder, you're just thinking of Z as some compression, some random compressed file. But here's the VAE. Now the VAE has a model of the joint distribution, which is defined by this probability distribution over the latent variable and the probability distribution over the evidence given the latent variable. So this would be the word sequence and the sound wave given the word sequence. But these three pieces are all just pieces of a model, right? And this optimization problem is going to be the same if I use different names for those pieces of the model. So I'm just going to rename them. Okay, I'm going to remove the hat from here and put hats on here, on these two. And it doesn't matter what I call them. The optimization, if it's the same model, it's the same optimization problem, right? So I can rewrite it down here. Now, this is exactly the same optimization problem. But now I'm going to define a different joint distribution. Rather than defining the joint distribution by p phi of z and p phi of y given z, I'm just going to consider the joint distribution defined by the population on y and the encoding into z from that population draw of y. So I'm flipping it around. I'm saying I've got a population on y and a probability of z given y. And this is a probability of z given y right in the variational autoencoder model. So I'm just taking that to be the definition of the YZ distribution rather than these. It's just a definition. It's the same optimization problem. And if I interpret it that way, if I consider the joint on z and y defined by drawing y from the population and z from the inference model, then this term becomes the mutual information under that distribution. So now this is a channel capacity. This is how many bits of information went from y to z. So that becomes a rate in exactly the sense of the rate distortion autoencoder. And then you can interpret this as a kind of distortion. So what I've just said is that a variational autoencoder and a rate distortion autoencoder are essentially the same thing if you interpret this as a distortion. And I'm going to pick that up in the next unit. So thanks.